Hello and welcome to our presentation. My name is Nathan and my fellow presenters are Morgan and Vidya, and our advisor is Dr. Martin Hahn. The title of our project is Building 3D Printed Surgical Inserters to Deliver Microelectrodes to the Spinal Cord for Severe Spinal Cord Injuries. There are more than 250,000 individuals in the United States that suffer from spinal cord injuries. These injuries can lead to the loss of nerve control of different organs, including the bladder and colorectum, and can cause a loss of sexual function. Many patients struggle with associated pain that make their daily lives difficult. Intraspinal microstimulation is a procedure in which microelectrodes are implanted into the gray matter of the spinal cord. This is done to enable direct contact with specific neurons. This method has been proven to help recover lost motor function and organ control, which ultimately improves the patient's quality of life. The goal of our project is to design an insertion device with integrated instrumentation for microelectrode implantation and a tissue model for testing. The insertion device was modeled using SolidWorks and had 4 prints of the various design improvements made. It features several key pieces, namely an internal spring for driving and damping, a wire inserter rod, a vacuum attachment point, and attachment points for the force and displacement sensors. It also features a trigger and locking mechanism to hold the spring in place. The design shown on the left hand of the screen represent the original concept for 3 parts of the inserter, which started out as a brain tissue inserter and has been repurposed for spinal cord insertions. The right-hand side designs are the optimized versions featuring finer details, functional improvements, and improved connections. The upper and middle images are 2 pieces that work to hold the displacement sensor body and rod. Changes were made to make it easier to secure the sensors to their attachment points. Finally, the trigger attachment shown in the bottom image was turned into a working pivot point that will hold the trigger in place and allow it to function properly.
The optimal design for the instrumentation portion of this project includes a force sensor to measure the force of the insertion and a displacement sensor to measure the distance of implantation. To analyze the data, a high-performance microprocessor will be used to convert the data from analog to digital and display the results. The instruments on the screen have been chosen because they fit the specifications needed for the project. The circuit design includes both sensors and the STM32 microprocessor. For the simulation, the force sensor input will be a negatively clipped sine wave, and the displacement sensor input will be a positive linear slope. These signals were designed to mimic the activity of the sensors during testing. The input signals for the sensors are connected to the internal ADC of the microprocessor, which is programmed to convert the data from analog to digital and produce a binary number. Then it outputs the 12 bits to the GPIO pins in order to display the ADC voltage. The video is in slow motion and typically happens in about 3 milliseconds. Binary waveforms for each of the 12 bits are generated and combined into a single graph in Excel. These graphs show the analog input and digital output for the force sensor and displacement sensor. The analog to digital conversion was successful and accurately represents the input signal of the sensors.
Originally, a SolidWorks model of the spinal cord was printed to be able to create a silicone rubber mold to develop multiple copies of the spinal cord for testing. However, testing of the tissue model was simulated on the ANSYS mechanical platform, and the results from the simulation will be highlighted. These are the stress and strain results from the simulation. Here is the strain, and here is the stress. This is the current simulation of the inserter traveling into the gelatinous tissue model created on ANSYS. The stress and strain simulation show the tissue reaction to the inserter device reaching the gray matter. As it is right now, the inserter device is traveling incredibly well into the model without deforming too much of the area around it, and it is not causing neither too much stress nor strain on the model. The videos above show that there is very little overall deformation taking place when the inserter pierces through the white matter and gray matter at a speed of 1 meters per second, indicating that our measurements taken for the construction of the inserter prototype will yield reliable. Major work for this project would primarily include developing a consistently functioning prototype with the insertion device integrated with the sensors. This should be tested with how well it can work with a stereotaxic frame, and the prototype should be tested on a tissue model. Multiple tests should be run on various models to be able to account for any inconsistencies and further develop the prototype. Later on, trials on animals using medical-grade design should be run to test the inserter prototype on a live model and record physiological data. The models and data presented show that this design and testing regimen can be implemented, but physical testing of a working prototype is the next big step. Only after extensive validation and verification of the physical prototype can we hope to begin animal trials, but the design work on the testing apparatus, tissue model, and inserter are the ideal foundation for work that is very iterative and incremental in nature.